Hi everyone, this is another test. As I made a chess game in C Sharp, in Unity, called Chess Tools, I'm kind of, well, I don't know, not really an expert, but I made a chess engine in that. I know how to do it, and I thought it's a very good way to test performance. So I decided to do it in lots of languages. So this is basically me converting my bitboard chess move generator into loads of languages just to test performance and also kind of compare how easy it is to actually implement such an algorithm in different languages. So first I should say performance isn't everything with languages. It's normally a cost benefit analysis which language, languages are used for different purposes. It's not just performance. For example, Python is extremely slow, but it's also very practical, easy to use, and has lots of really practical libraries. So it's not really speed that's the point. Whereas C++, the whole point is speed, so it kind of depends what the purpose of the language is, and also if something's ridiculously hard to learn, but its speed, it's kind of like a trade-off between those things. So the speed isn't everything. Also, this is a very specific task that's very, very CPU intensive. Most tasks aren't this intensive, and you don't need this much speed. Here's just an explanation of how the bitboard algorithm works. So here we have a basic chessboard, and we want to represent this in code. So normally what we'd use is just an array. So we use a 64 element array like this with integers, and then we'd use these constants to index them. So it looks something like this, well, of course the 12 being in between for the empty squares. This is how we'd normally do it, but this is not the approach I used. I used bitboards. So what are those? So as the chessboard has 64 squares, we can represent them as unsigned 64-bit integers, like this in C++, unsigned long long, bitboard equals 0u long long. So let's say we want to represent these knights. So these will be basically 57 and 62. So we need to put the 57 and 62 bit set. So we do this like this, explaining how this works. So we have the bitboard empty with no bits set. And then we have one u long long, which is the first bit set. What we do is we shift that bit 57 places. That basically just sets it to the 57th place, and it gives us this value. And then we do what's called ORing. And what OR does is basically if one of the bits is set in either bitboard, then it will set it in the result. So bitboard will be set to this. So we put a 1 there. So the equivalent of putting a 1 in the 57th place. And do the same with 62. So we put 62, OR it with this, and we've added 62, and we get this long number. You don't care about the number, you care about the bits. So we've set the bits there. So we're now representing the white knights. However, we can't use one integer for all 12 pieces, as you need to tell the difference between them. So instead we use an array. So unsigned long long board array by 12, and then we use the indexes before to index them. So in this position, let's say for example we want to get the knight move, so white. So from this square here. So first we'd copy the knight bitboard, and then we'd get the square. So we scan basically looking for the lowest square in bits. Then we've pre-computed the knight attacks for every square. So every square will have the pre-computed knight attacks, and this will be 45. So if we look at 45, it shows this. So this is the knight attacks from this square. But now we have to get the occupancies. Basically, we want to know where the white pieces are, where the black pieces are, where both pieces are, and where the empty squares are. And we get the black occupancies by ORing all the pieces together. We get the white occupancies by ORing all the white pieces together. We get the combined occupancies by ORing them both together. And we get the empty occupancies by not operator on the combined occupancies. And the not operator, the squiggly line, will basically invert the bits. So if it's occupied, then we'd want it to be not occupied. And these look like this from this position. So what we need to do is use these and compare them with the knight attacks. So we use the knight attacks and we compare them. We compare them with the AND operator, using the AND sign. And this basically means if both of the bits are set, then it will set the bit in the result. So here, this will give the result. Capture moves will be this, because that's the bit that's set in both of them. So now we have a capture move for the knight. And then we do the same with the empty bitboards, the empty occupancies. And then we add those together and we get the regular moves. So these are non-capture moves. And this is basically how you do it. In code, it will look like this. So we get the bitboard, and then while it's not 0, we get the square, and then we basically do this, which just removes the least. It's a very simple way to just remove the least significant bit. Then we get the knight moves again by ANDing it with the anti-occupancies. We make sure that's not 0. We get that square, and then we remove that, and then we add the move to the move list. Do the same with the captures, with the black occupancies. Make sure it's not 0. Get the square, remove it, and then add it. That's basically how the algorithm works, but with every other piece as well. So limitations for languages. You need to be able to do bitwise operations. If you can't do bitwise operations, you can't use it. You need to be able to use unsigned 64-bit integers, which rules out a lot of the languages actually, because if it's not strongly timed, doesn't have unsigned integers, you can't use it. You need to be able to use large constant arrays. That also rules out some languages. And you need to be able to do recursion. All right, I'll show the C++ code first. You have the board array, basically. You can have it in a struct, or you can have it separately. So you can have it globally like this. I think I tested both, and it basically gave the same results. So I hate header files. I can't be bothered to do it. I just put everything in one file and just use regions. It's 10 times easier. I don't have to deal with linking errors that way. But anyway, so I just test both of them. I'll show you. The results will be a bit less than the actual final results. So I have to hit enter for it to start. 0.49, 0.46. It's basically the same. Doesn't really matter. So global or not global doesn't really matter. So I set the starting position, and then I copy into like a copy of the global variables anyway. So I call perf inline global. Basically the difference here is that here it's using the global board, here it's using the struct, but they basically have the same results anyway. So I've loaded temporary variables that I used basically just to generate moves. I have pins and generate moves. I mean, the basic algorithm is simple, really. Just get a position, generate the moves, play each move, go to the or make the move, then go to the next. Well, call the function again recursively, and then they play their moves until you reach basically the limit, which will be when the depth is 0, or when it's 1, you return the move count, which is an optimization, because you could make it 0, but that makes it slower. So basically you just -1 and call it recursively. Make move. You basically just play the move, play the move, play the move, play the move. Oh, it's down. The depth is 0. Okay, return the numbers. That's basically what we're doing. And the number we get, so the number we're looking for is 119,060,324. That's what we're looking for. Now, there's not really too much to note on the C++ code. I'll show you the constants. The constants are massive, absolutely massive. So the De Bruijn method is how we get the least significant bit. I don't really understand it, to be honest. I kind of got. I used a tutorial on how to make this, which I can put in the description. So I use the De Bruijn method to get the least significant bit, because in theory what you could do is like scan each bit and then see if it's empty or not, but that's slow. So this is the fast way to do it. And I have a load of massive arrays. So I have the white pawn attacks, I have the black pawn attacks. Like basically for every piece. The ones that are really big are the rook attacks and the bishop attacks. Because it's kind of complicated to get the bishop attacks and rook attacks because they go. It's not like a knight or something. They go until they get blocked. So you basically have to use this like 64 by 4,000 array, and then use this really weird complicated function. You get rook attacks fast, and you do loads of bit shifting. I don't really understand how this works. I just kind of copied it. Converting it over to Rust and Zig was a pain in the ass, though. Anyway, so that was the C++ code. Okay, so now we have the C# code. Just have console.readline just so it loads, and then I do everything. So perf run. So I think in the C++ I used a board array. I would just create the board and then pass it in. I'll give them, I use span as well, stack a lock, because I don't want it to heap allocate because arrays are on the heap in C# by default. So I want it to be on the stack. And I made it 50 just because I tested the 50. It doesn't actually go above 50 ever in the actual average moves. But other than that, it's basically the same. Generate moves is quite big as well. It's quite a lot of code actually, all this. That's why I put it in regions. I'm just showing an example of one of the, say for example, the White Knight. It's basically what I showed you, but it's a bit more complicated because I have pins and check. It's like, say if it's check or if it's pin, I basically AND it with that as well. So basically I'm ANDing it with the black occupancies to get the captures, and then I'm seeing if it's ANDed with check and ANDed with the 10-bit board, pin bit board, to see if basically, if it's pinned, it shouldn't be able to move. That's basically what I'm doing. It's a bit complicated to explain that, but that's the basic example. And the C# is basically the same as C++, it's just less fast. Alright, next we have Go. Actually, I didn't like Go before I actually started this, making these. I actually really do like Go. It's very simple. Basically, Odin is basically like Go, but with like manual memory management. There's not really too much difference actually between them. But the package system is just great in Go. It's just really easy to make everything work. Go is very, I mean, it's surprisingly fast actually, considering it's garbage collected. Anyway, so the Go code is pretty simple, really. I do exactly the same thing: load fen, print the board, and then run perf in line. Go to here. So everything's pretty much the same. You have uint64 is basically the 64-bit unsigned integer. I have generate moves. There are no regions in Go, so I kind of have this like massive code showing. Like that. Okay, that's generate moves. I'm not sure why I can't close this. It won't let me, but I would if I could. And the rest of it's basically the same. There isn't really too much difference. What's surprising, though, is the results of the Go code, which I'll show you the results at the end. So the Go code is actually very easy to make. It took me about maybe 1 to 2 hours, basically. I just copy and pasted over from C# and then just change the names. Also, I kind of use the module system quite a lot in Go, just to split things up. So I have the bitboard constants, I have the move constants, which are absolutely massive again, massive arrays. I split it up, but Go was very easy to use, and I actually really do like Go, and I would probably recommend it for any beginner, actually. Alright, next we have Zig. Alright, Zig was actually a really big pain to get this to work, just because Zig has very strict type system. So the main problem I have with Zig, if I can find it. Okay, so bits going forward, I have this really so the problem is the bits going forward actually has an overflow. It has an integer overflow. So either you need to make basically this a U128, 128 bits, or you have to use this to specify that it's an overflow and you don't care about the overflow. And then you got to truncate it down to U6 because De Bruyne uses, it's a 64-bit integer and 6 U6. Basically, either you make it a size, or you make it a U6. And I had to convert these into U6s. What else? So I think I use U6s in the actual perfed test. So bits going forward is a U6 and a U6, and then these are U8s. So I think I put a U6 into a U8, which is fine because it can go upwards. And I'm using U6s in lots of these just because just annoying. But actually, it's more annoying in Rust actually because you can't use unsigned integers for indexes. You have to use a U size, so you can't just use a U6 or U8 and use the indexes. You have to use a specific U size, which is kind of annoying in Rust. Get bishop attacks fast is also ridiculously annoying because it has an integer overflow again, which is always fun. So basically, you have to so you send the occupancy over, and then you bit shift it with stuff. So you have to make a copy of it because by default they're immutable. So you have to make a copy of it, and then you shift amount, which is a U64, because the U64 has to be the same. You can't just use an integer. And then we and equals that, and then we have another overflow. So we use the percentage sign to ignore the overflow. Then we truncate this. I'm not sure why we're truncating this. That's a good question. By the shift amount, it's U64. I actually have no idea why I'm truncating that. And I truncate the mutable occupancy into whatever the size is. I don't know, I had to use a lot of truncating, otherwise the compiler kept annoying, like saying, oh, that's wrong, don't do this. And It was very frustrating to get this to work, but eventually I did. I use a struct here as well, but the thing is, like, with the C++, it was basically the same performance with or without, with global variables, so... Okay, now we get to Odin. So Odin was probably the easiest to get to working, because it's basically the same as Go. You just copy and paste the Go code, and then change everything to, instead of func, whatever, you just do procedure, and basically it works. So some weird thing with Odin, if you create basically a constant, I don't know why this happens, it's very weird. So if you make this constant like this, it will give you errors. So you have to make it mutable, and then you have to use this @read-only data to make it not mutable. It's kind of weird, I don't really understand why that happens, but it's just a weird thing with Odin. Other than that, I have basically no problems. I've had some bits come forward, didn't have any problems. There was some kind of problem I had, but yeah, it was mostly that, I think. Anyway, so Odin, yeah, very easy to get working. It was pretty much the same as the Go code. You just change everything to procedure, and then it works. Everything uses the same package system with Go. And yeah, that's pretty much it. There's nothing really I can say else about Odin. And now here comes the meme section. So this is Python. I don't like Python at all. I'm going to wait for this to load. Okay, it's loaded. I don't like Python at all. I like to write semicolons, and I like to use curly braces. So I wrote probably the most passive-aggressive Python code you'll ever see in your life. So I have, well, first of all, I should say, you can't actually natively represent a uint64 in Python. So what you got to use is NumPy, and NumPy has a thing, uint64. If I show you here, for example, well, you got to do it like NumPy array, and then the whole array is massive. And at the end, you specify what the type is, which is kind of annoying. I mean, look at this massive constant. D-type numpy uint64. So you've got to specify. These are user ints uint64s. That's the only way I've found to do it in Python, because obviously it's not strongly typed. We'll have all these massive constants. They're all np array d-type uint64. And now we come to the most passive-aggressive Python code you've ever seen in your life. I couldn't be bothered to delete all these, and I don't like indentation, so I just basically put the curly braces with a comment, and it works. And it's quite a lot easier to read for me, honestly. Then I also have semicolons. Bitwise operations work in Python, which is cool. And everything is np.uint64, np.uint64. Everything else works basically the same. I mean, you wouldn't even notice this is Python unless you see like there's a colon here, but curly braces makes everything readable. I know there's a mod of Python that makes you can use curly braces. I couldn't be bothered to install it. It's easier just to use memes and just do this. Anyway, yeah, so Python was pretty slow actually, but I got it working. I mean, other than that, there's not really much difference. I mean, recursion works pretty well, and yeah, it's pretty much the same. Alright, and here we get to Rust, which was easily the hardest to get working imaginable. I'll try not to make this a rant, but oh my god, this took me about 3 days, and a lot of debugging, a lot of spamming ChatGPT to get this to work. So what's the main problem? I'll show you. Okay, I'll show you what happened. So I just made a PowerShell in this window, cargo run. Get loads of warnings because of the names. Oh, what's this? Thread main has overflowed its stack. What? Why is it when it's overflowed its stack? In every other language, it didn't overflow its stack. Why would it have a stack overflow? Oh, because we're in debug mode. And for some reason, Rust has a very, very limited stack size in debug mode. Which is very stupid because it's supposed to be a language about safety. Let's have a language about safety, have a limited stack size so you can't run it in debug mode. What? Are you stupid? Do you, like, what? Who designed this? Like, honestly, why would you have a limited stack size? This is a recursive program. Also, like ChatGPT explained to me, all these constants I have get put onto the stack. So you have, like, literally, all of these constants are put onto the stack. So I'm putting on a 4096 by 64-bit array, 64-bit array on the stack. Of course, it's going to stack overflow. What? And I actually, like, I basically tested where it gave the stack overflow is exactly when I get the rook attacks. You know, get rook attacks fast, it would give you a stack overflow on this line every time. So it basically puts this onto the stack and doesn't realize that it's an array, get one element of the array, put that on the stack? Why are you putting the whole array on this stack? Apparently, in debug mode, that's how Rust works. So it gets you Stack Overflow. So if you have a bug, good luck trying to find it, because you can't run it on debug mode. The only way I could run this program is in release mode. It's the only way I could get this to work. So here's what I did before, basically trying to get it to run on debug mode. I made them lazy static and made them boxes. Obviously this will be heap allocated. Trying to put it not on the stack, it still gave me a Stack Overflow. So cargo run, release, and it works. It doesn't give you a Stack Overflow. So that was one problem with the Rust. Then I tried to separate it into modules. But then I found the module system is terrible. It's absolutely terrible. I don't know why they designed it this way, because everything's interconnected. So you say, for example, you have like, I don't know, you have the main script, then you have the board script, and then you have the constants, and then you have, I don't know, the perf script, and they both want to go to constants. But then he says, Rust compiler says, oh, you have to put this in a folder called board if you want to use it here, but then you can't use it from perfed. It's like, why is this so complicated? I don't care, I'm just going to put everything in one file. So I put everything in one file, and it's like thousands of lines. Because I just want things to work. Rust is basically the language you don't want to use if you want to get things to work quickly. And then here we go with get rook attacks fast was really goddamn annoying. So the occupancy, again, is immutable, so you have to make a copy of it, let mute mutable occupancy. Converted starting index is a use size. I don't remember why I made it a use size. Debugger set doesn't work there anyway. So mutable occupancy. Yeah, I mean, it's not that. It wasn't that complicated. This change. I basically had to make this mutable using let mute, and I had to make this a U size. So it basically truncates it so it actually fits. And also you have to make these U size because you can't use the starting square I32 as an index. So you got to make it a U size. Then the bit scan forward is also pretty annoying because it has an integer overflow, which I guess you could ignore in release build, but I was getting compile errors in debug mode before I got the Stack Overflow, so I basically just made it a U28, and then made it a U64 after that, and then made it a U size, so you can put it in these indexes. It's quite annoying to do this when you don't really understand the algorithm, you didn't make it yourself. Alright, so other than those complications and getting loads and loads of bugs that I couldn't fix because debug mode didn't work, I finally got it working. It's relatively the same, honestly. There's not much difference. The main problem is just... Right, so another problem is you basically have to make everything a U size. So I get an I32 from the bit scan forward. I guess I could have made it a U size. I don't know. I didn't make the algorithm, so I don't know. So I just converted everything to U size, as U size, as U size, as U size. As you size, literally as you size in every goddamn thing here. As you size, as you size. Here, as you size, as you size. That's, yeah, just annoying. That's Rust. So I should say the way I got these results, I basically ran the test 5 times and then divided by 5 and to get the average. Right, so finally we have the results. So Python, yeah, Python was about 22 minutes. It's quite a long time, honestly. Obviously Python isn't really used for performance. Also Python has a problem with global variables, but I wasn't sure even if you could make a struct and then insert it by reference into a function. I don't even think this, it's just Python isn't really there for performance. It doesn't matter if you optimize it at all. C# was relatively slow in comparison with the others, but it's a garbage collected language. It's also JIT compiled. So it's not exactly going to compare with any of the others. Go was surprisingly fast, considering, again, it's a garbage collected. And it's what, 20-30% slower than the non-garbage collected languages, which is pretty impressive. So Rust, Odin, and Zig, fairly comparable, honestly. Considering how easy Odin was to do, like Odin was probably the easiest, but considering the performance of Odin, like it's the obvious choice. It's easiest to use, and it had basically the same performance, so why not choose that? And I have no idea why C++ is so fast. I don't understand what it does that makes it so optimized, but that's the results I got. I don't really know exactly. So I did try to use Java, but Java doesn't have support for unsigned longs, unsigned 64-bit integers. So basically it's not really possible. You'd have to make everything a big integer and then put a whole array full of thousands of elements with big integer equals. Not doing that. Same with nim. I tried using nim. No chance of my doing that, honestly, because you have to use big integers. It's the only way to do it. Yeah, it's not feasible. And it's also the same with JavaScript, I believe. JavaScript would have to use big integers as well. So if it doesn't have native unsigned integers, it's very hard to make this algorithm work. But anyway, let me know your thoughts on this. Thanks for watching.